Welcome viewers to the 8th lecture for the online series of lectures for the course of linear algebra. In this lecture, we are going to study matrix representations of linear transformations from a finite dimensional vector space to another finite dimensional vector space defined over the same ground field F. So we are concerned with a linear transformation T from an n-dimensional vector space V to an m-dimensional vector space W defined over the same ground field F. So V is an n-dimensional vector space and W is an m-dimensional vector space. So they are taken to be defined over the same ground field F. This is defined over F. Okay, and we'll see that the set of all such linear transformations so if we consider this set of all such linear transformations, then an element here is in one-to-one correspondence of an element in this set. This is the set of all m times n matrices over this field F. Okay, so if I have a linear transformation here T, we can find an m times n matrix A in this set. Okay, so it is in this sense we say that A is a matrix representation of this linear transformation T between finite dimensional vector spaces V and W. Okay, so we are going to study these things in detail and results concerning these notions. To do that, we first need the concept of isomorphisms um, between finite dimensional vector spaces. So let me define it first. If V and W are vector spaces over the field F, any one-to-one and onto linear transformation. We want this transformation to be linear. So any one-to-one and onto linear transformation from the vector space V to the vector space W is called an isomorphism between V and W. Okay, if there exists such an isomorphism, isomorphism I should say is called an isomorphism from V to W. Okay, so if there exists such an isomorphism between V and W, we say that these two vector spaces V and W are isomorphic to each other. V and W are isomorphic. Okay, now as an example, note that V is trivially isomorphic to itself. So what is an isomorphism between these uh, uh, isomorphism from the vector space V to itself? The identity transformation, or the identity operator on the vector space V. So note that V is isomorphic to itself. It's a trivial thing, and the identity operator I is an isomorphism from V to itself. Okay. Now I leave it as an exercise for you to verify that isomorphism is an equivalence relation on the class of vector spaces over a given ground field. Okay. Verify that isomorphism is an equivalence. You have to verify that it's reflexive, it's transitive, and it's symmetric. An equivalence relation on the class of vector spaces over F. Okay. Now we have our first theorem of this 8th lecture. Let me erase everything and state the theorem first, and then I'll sketch the proof. Every n-dimensional vector space over F is isomorphic to F to the n. Okay. We have seen consequences of this result in previous lectures. So let me sketch the proof. Let V be an n-dimensional vector space over the field F. Okay. And let B be an ordered basis for this vector space V. We define a function T from this vector space over F to F to the n as follows. Okay. We are going to define this function. If U is any vector from this vector space V, let Tu be the n-tuple x1, x2 all the way up to xn, n-tuple of coordinates of U relative to this ordered basis B, relative to the ordered basis B. Okay, that is um, the n-tuple is such that that is the n-tuple satisfies the following relationship. U vector has a basis expansion like in this way, right? And we know that this expression is unique. Okay, from which we find that the coordinate matrix of this guy is indeed this n-tuple x1 x2 all the way up to xn. All right, so when we pick up the vector u from this vector space, tu is going to be this n-tuple, that unique n-tuple in f to the n. Now I want you to verify that t from v to f to the n defined this way, defined by tu is equal to x1 comma x2 comma all the way up to xn. This map is linear. This is 1 to 1 and this is onto. Okay, so this expression is unique and hence it's 1 to 1, right? So the well, no two vectors of v can have the same n-tuple as its coordinate matrix, as their coordinate matrices relative to the same ordered basis B. Okay, so if I take two distinct vectors from this vector space with reference to this ordered basis, they cannot have the same coordinate matrix. It can never happen, which means that this map is 1 to 1 and you need to prove that it's onto as well. Okay, so now I suggest some more exercises from the book by Hoffman and Kuhns. Suggested exercises. Problem number 1, problem number 2, A, B, and C, all three parts. Problem number 3, problem number 4, and problem number 6 from page 85 to 86. Okay, so they're suggested from the book by Hoffman and Kuhns. Okay, good. Now we come to our important notion of representations, representation of transformations, transformations by matrices. Okay, so in the beginning of this lecture I gave you a hint of what is meant by representation of linear transformation from a finite dimensional vector space to another finite dimensional vector space, both defined over the same ground field F. Okay, so let me describe that thing in detail now. Let V be an n-dimensional vector space over the field F, and W be an m-dimensional vector space over the same field F, so that we can talk about linear transformations from one vector space to another vector space. Okay, we also need a few more data. Calligraphic B, which is a set from U consisting of the vectors u1, u2 all the way up to un. Let this set be an ordered basis of for the vector space V, and calligraphic B prime equal to the set V1, V2 all the way up to Vm be an ordered basis for W. Okay, so W was taken to be an m-dimensional vector space and V was taken to be an n-dimensional vector space, right? Now, if T from V to W is a linear transformation, if this guy is a linear transformation, then T is determined by its action on the elements of the basis UJs, where J runs between 1 and n. Okay. Now note that each of these n vectors Tuj, right, is uniquely expressible as a linear combination of these m elements in the ordered basis B prime. Okay, why? Because Tuj is in W here, and W has B prime as its ordered basis. So Tuj can be written as a linear combination of these elements in B prime. So let me write this expression of linear combination Aij Vi, where I runs from 1 to m. Okay, so if I'm picking up this vector uj, then I can write it as a1j v1 vector plus a2j v2 vector all the way up to amj vm vector. Okay, so um, so here j runs from 1 to n. So there will be, there will be n such linear expressions, right? Uh, so the first one is tu1, then we'll have tu2, and then all the way down to tun. Right? So the scalars here, a1j A2j, AMJ, these guys being the unique coordinates of TUJ vector relative to the basis B prime. V1, V2, Vn. Okay, good. Uh, Let me write it using coordinate matrix. So we have seen that if I pick up this one of these n vectors tuj and I express tuj in the basis b prime, then the coordinate matrix of this vector tuj is going to be a1j, a2j, all the way down to amj, right? So the linear transformation T, so this is the jth column of our matrix A, right? And whose entries are Aij, and these entries, you know, constitute the matrix A, which fully describes these matrix T relative to the pair of ordered bases B and B prime. Okay, so this so if I take the first column of this matrix A, that is going to be A11. I just plug in J to be 1 here, so I have A11, A21, all the way down to AM1. Then I can have the the second column, and this is going to be A12, A22, all the way down to AM2, right? And then I can have the last column here, which is A1. So J runs from 1 to n, right? J is between 1 and n. So the last column is going to be A1n, A2n, all the way down to AMN. So this is the matrix A that represents the linear transformation T with reference to the pair of ordered bases B and B prime. Okay, let us try to understand more explicitly how this matrix A determines this linear transformation T, okay, in terms of its action on a given vector u of the vector space V. Suppose we choose a vector u in V, and we know that B is an ordered basis of this vector space, right? Which consists of these n vectors u1, u2, all the way up to un, and W is an m-dimensional vector space which has this ordered basis B prime consisting of these m vectors v1, v2, all the way up to pm. Okay, Now, if I pick up this arbitrary vector u from the vector space V, then we can write it as a unique linear combination of these basis vectors. Okay, so um, let us write that linear combination as x1 u1 vector plus x2 u2 vector all the way up to xn un vector. Okay, so u vector can be uniquely expressed as a linear combination of these n vectors, right? Now I write t acting on u, that uh, is nothing but t acting on this expression, which I write using sum notation as sum of all the expressions such as xj where j runs from 1 to n. Now using the linearity property of t, we can rewrite this expression as xj times t of uj by linearity of t, and then um, we have seen earlier that this guy t of uj is nothing but this expression, right? I from 1 to m aij vi vector. Now I exchange I swap these two summations. So one is summed over I and the another one is summed over j. So I swap these two summations. So I bring the I sum outside and take the j sum inside, j from 1 to n, and I have j appearing in aij and xj, and then sum everything over I. Okay, this is, I number this equation by 3. Okay, now remember that u was expressed uniquely as a linear combination of these n vectors. So mm, um, I denote the coordinate matrix of the vector u relative to the basis, relative to the ordered basis calligraphic b by x, so that x is equal to um, these n tuple, right? x1, x2, all the way down to xn. This is x. Right? So in our notation, x is going to be the coordinate matrix of u relative to the ordered basis b. So now notice that when you write this guy ax, right, this is going to be a column vector. This is going to be a column vector. So if I denote the the column matrix as AXI, where AXI is one of um, the entries in that column. Okay. So what is A? A is an M times N matrix, right? M times N matrix, and we have seen that X is an N times 1 matrix. So AX is an M times 1 matrix. Okay. So I runs from 1 to M. There are M such entries. So we know that it is nothing but sum over all J's, where J runs from 1 to N, and this is I, J, X, J. Okay. So this is AX sub I. So you can verify it directly by putting the matrix form of A and X. Suppose, so let me give the details. A11, A12, all the way up to A1n, right? That's the first row of the matrix A. The second row is A21, A22, all the way up to A2n. And finally, I have the mth row AM1, AM2, all the way up to AMN, right? And now I multiply it with the matrix X. So there are n entries here because it's an n times 1 matrix. So what will be the it is going to be an, so this is m times n, this is going to be n times 1, so this is going to be a column vector m times 1. So there will be m entries here in this column. So the first entry is A11x1, then I have A12x2 plus all the way up to A1n xn. That's the first entry. The second entry is A21x1 plus A22x2 plus all the way up to A2n xn. Okay, and finally one has this entry am1 x1 plus am2 x2 plus all the way up to amn xn. Okay, so this is the matrix AX. Okay, so the first entry is AX1, this guy is AX2, and this guy, the final one, is AXM. Okay, now verify that it is indeed this expression, right? So in other words, this is going to be AI1x1 plus AI2x2 plus all the way up to AIN xn. This is indeed what we have here. This is the first one. So A11x1, A12x2, and A1n xn. So when we take the second row, it's going to be A21x1, A22x2, and then all the way up to A2n xn. When we take I to be m, the mth row of this column vector is going to be am1x1 plus an2x2 all the way up to amnxn. Okay, all right, good. So we see that if we write if we denote the coordinate matrix of this vector u in the ordered basis b by x1, x2 all the way down to xn, then and this is going to be, we are denoting this guy by x. Okay, so the m times n matrix acting on this column vector x is nothing but this expression where j runs from 1 to n. This is going to be aijxj. Okay, this is what we have seen. So now tu vector, we have seen that tu vector according to equation number 3 is this. There were two summation, one is over I, then whatever we have inside is summed over j, where j runs from 1 to n, and this expression is aijxj, and whatever we get here gets multiplied with the vector vi, and then we sum over all i's. That was equation number 3, right? Now from this we know that this guy, in according to our new notation, is axi, so that we have sum over all i's axi vi vector. This is our equation number 4, where axi is the ith row of the m times 1 matrix ax. Okay, that we have discussed earlier, right? So in our notation, x is the coordinate matrix of the vector u relative to the basis b, and well, and we have seen that so what is this vector ax is this, right? ax1, ax2 all the way down to ax. Ax is an m component column vector, right? axm, that is ax, right? And from 4 we see that this is nothing but the coordinate matrix of the vector tu relative to this basis b prime, right? Remember that b prime was this ordered basis, b1, v2 all the way up to vn. So this is clear. Ax is equal to the coordinate matrix of tu relative to the ordered basis b prime. Okay, good. So let me write it in words. Ax is the coordinate matrix of tu in the ordered basis b prime. Now, in the other direction, if A is any m times n matrix over the field F, if A is any m times n matrix over the field F, then define T by T acting on this vector of the vector space V, right? And I'm defining, this is defined as this expression, using this expression, which was our equation number 3. I'm just rewriting equation number 3. Okay, from I from 1 to m, and then sum over all j's of these expressions aij xij, and multiply those expressions with vi, and then sum over all i's. Okay, so this is our equation number 5. So if I am given an m times n matrix A whose entries are these aij's, each aij is in the field F, okay, and I define this transformation T from the by this expression, it's clear that this guy, since these vectors constitute a basis of the vector space V, this vector is in the vector space V, right? And this whole thing is in the vector space W. Why? Because these V1, V2, all the way up to Vm is an ordered basis of the vector space W. So T defined this way is indeed a transformation from the vector space V to the vector space W, given these two ordered bases of the vector space V and W respectively. We know that these are two ordered bases of the vector space V and W respectively. Hence, T defined this way is indeed a linear transformation, is indeed a transformation from V to W. Now, one needs to verify that it is indeed a linear transformation. Okay, so let us see how we can verify that it's a linear transformation. I think I could leave it as an exercise, but if you want, I can write down the proof. It's a trivial task, but let me do it for you. So T acting on two vector C times this vector plus another vector of the vector space V. So let us denote that vector by y coordinates, yj uj vector, j from 1 to n, right? This is vector V. Okay, let us denote vector V by this. Then T times T acting on C times this vector U xj uj, where j runs from 1 to n, plus yj uj, where j again runs from 1 to n. Okay, this can be written as T of, I can take this C inside, Why? Because C is an element of the field F, and UJs are vectors in the vector space V, and V is a vector space defined over the field F. So I can take C inside and um, do whatever I want here by multiplying C with the scalar xj, right? So I'm taking C inside the sum Cxj uj, and then the other summand over j y yj uj. Okay, I can do that. Now I can do some algebra, a little bit of algebra here, using the vector space property of V. Everything is happening inside B, is inside the vector space V here, in whatever we have inside the bracket. So we can do some use the properties of vector space to do this little algebra. Sum over all j's, Cxj plus Yj uj. And now I invoke the definition of T here, right? According to this definition 5, this is equal to um, sum over all i's and then sum over all j's, and what are the aij's? I have to plug in aij because that is in the definition, and these are the xj's, so I have to bring xj's. So xj is this whole thing here, right? So cxj plus yj, right? That's the xj here. I close the bracket and then I have to put vi vector. Is that correct? Right. Now I have to separate distribute this sum into two parts, and let us bring this C outside. C times sum over all i's, then inside bracket I first put all the j sum aij xj, and then the vector vi plus sum over all i's, right? Then sum over j's, j from 1 to n, aij yj vi. Okay, so I just distributed these two sums into two parts. That's what I have done here. Okay, so according to the, now I invoke the definition 5 again to write this as C times T acting on this vector xj uj vector, where j runs from 1 to n, plus for this expression, remember that this is v, so this is according to this definition, um, So these XJs comes from the fact that uh, we write U as as a sum of all the expressions like xj, uj, where j runs from 1 to n. Okay, so when we have uj, xj, uj here on the right side, after the action of t, I just have the coordinates xj. So now um, we had this right hand side, which means that t was initially acted on uh, yj, right? Sum over all yj uj vector. Okay, so this expression is equal to this expression, meaning that T is indeed a linear transformation when I define it this way. Okay, good. This is what I wanted to verify. And so what I mean is that if I am given an m times n matrix over the field F, I can always find a linear transformation in this way from the vector space V to the vector space W. Okay, which means that it's correct in both ways. Okay, so if we are given a linear transformation, we can find an m times n matrix over the field F, and if we are given an m times n matrix over the field F, we can find a linear transformation P from the vector space V to the vector space W. Okay, now let us summarize all these results formally by means of a theorem, which we number by theorem 2. Let V be an n-dimensional vector space over F and W be an m-dimensional vector space over the same field F. Let B and B prime be ordered bases of V and W respectively. For each linear transformation, T from V to the vector space W, there is an m times n matrix A with entries in the field F such that Tu vector, when expressed um, in the basis B prime, has coordinate given by A times the coordinate matrix of U relative to the ordered basis B. Okay, so remember that we found earlier that AX was equal to TU B prime, but we have chosen X to be the, we denoted by X the coordinate matrix of the vector U relative to the basis B, right? So indeed the matrix A times this coordinate matrix U, coordinate matrix of U relative to the basis B, is the same as the coordinate matrix of the vector Tu relative to the basis B prime. Okay? This is what we wrote here. Okay, this was equation number 6. Now the other direction, and this holds for every U in the vector space V. Furthermore, T and A, this correspondence is a one-to-one correspondence, between the set of all linear transformations from V to W. On one side is this set, and on the other is the set of all m times n matrices over the field F. M times n matrices over the field F. Okay. So these are the two sets. An element of one set is in one-to-one correspondence to with an element in the other set. Okay. All right. So this was the statement of theorem 2, and we already proved it and summarized the result by means of this theorem. Let us take a break here. We will be back with more results in the next segment of the lecture 8. Thank you for attending the first segment of